Good morning. We start today's first morning session. It's my great pleasure to introduce Cristina Cornelio. Cristina is a senior research scientist at Samsung AI in Cambridge. He did profound research in the intersection of formal logic and machine learning, and her current work focuses on neuro-symbolic integration, reasoning, automated theorem proving, and scientific discovery. Okay.
Thank you, and good morning, everybody. And thank you for inviting me to present my work in scientific discovery at the workshop. Let's see if I can change it. Okay. So when we started to work on scientific discovery, so in this field, we started from the basics. So we started to look at the classic scientific method. But and we ask ourselves if this is still fit for purpose. So, but then we start to see more and more evidence that probably the classic way of doing things is start to reach its limit. So you can see here on the right, you can see my cursor? Yes. You can see here on the right, this is a study that was done in 2020 from the American Economic Review that shows that even though the number of researchers is increasing over time, the research outcomes are decreasing. So, and why is that? I mean, we don't really know, but one of the hypotheses is that all the low-hanging fruit of a scientific discovery has been already caught. So now we need to do something a little bit different if we want to continue to discover new things. So, and what does this mean is that probably what the human mind can discover by itself has already been discovered, and now we need some additional tools to help us. So, but what are the AI approaches for scientific discovery nowadays? So here I have a classification in four main branches of this. Of course, it's not meant to be comprehensive, but this is kind of my interpretation. So the first one is what we call data-driven discovery, right? So this is, we are just learning patterns over data, and we don't introduce any prior knowledge. And these methods are something like symbolic regression, neural network that approximate a function, or reinforcement learning for symbolic regression, and so on. So these are great methods. The problem is that we just look at patterns over data. We're not looking for something that is also physically, scientifically meaningful. And this is one approach. Another one that is a little bit more recent is what I call knowledge-aware models. So these models, the idea is to integrate some prior knowledge into what we are learning. And we can see many examples, like physics-informed neural networks, physics-sparse neural networks, equivariant symmetry-aware neural networks, and so on. And I think we'll see some of these examples later today from other talks, and maybe also yesterday. So these also are great models and very useful for many applications. But also these models, they have their own limitation. For example, they're hard to adapt, so if we want to change the constraints we are imposing, we need to change the network itself and train it again. Sometimes they only work with soft constraints, not hard constraints, and so on. So another category is neurosymbolic and hybrid approaches. So here also we try to bridge these two components of learning and prior knowledge using logic. So, and here we have logic-guided learning, inductive logic programming, program synthesis, and so on. Also, these methods have some limitation, like scalability, often works only on soft constraints and not hard constraints. And finally, the most recent is generative AI, so and agentic approaches. These are great in the fact that they use prior knowledge, so they integrate knowledge because they learned already this knowledge. So the knowledge is embedded in the models already. And we can see the use of LLM, VLLM, or agentic framework, the so-called AI scientists. They are very popular recently. The problem of these models is that they are prone to hallucination, which could be also a good thing, we don't know. And they don't have much scientific rigor. So, as you can see, there are many different ways to approach scientific discovery, and but the problem is that even if AI is beginning to transform scientific discovery as we know, like from the classic way of doing things, is creating what I call verification bottleneck. So because before we had only few hypotheses, and then humans, we verify these hypotheses manually, and we see if this makes sense, and this creates some new discoveries, right? So, but nowadays, the number of hypotheses is increasing exponentially, but the verification pipeline is the same. So we didn't change that. So the number of scientific discovery cannot increase if we don't change the verification part. And as you know, with agentic approaches, we try also to automate this part. But agentic approaches, often they're not reliable in the sense the verification is just a soft verification, so it's not like a formal logical proof. So just to give an example, we tried to recover the Kepler's law of planetary motion with the ChatGPT. So I don't remember which GPT-5 model we use, I think 5.2 or something, not the most recent one. So, but we introduced the data for the motion of planets on the binary star data set. So binary star is a star system where you have two stars orbiting each other, right? And planets around them. So, and we substituted the name of the variables with anonymous names. Otherwise, it's likely the GPT will say, okay, M1 is likely the mass. So we didn't want to give any hint or introduce any prior knowledge there. So as you can see, GPT produced a whole proof and tried different things. And the results is that it said, okay, this is the correct formula, right? Which is very different from the actual one, right? So as you can see with this model, even if you use agentic models, you can produce a lot of this formula that are not too bad, right? But also are not the correct one. So we can generate many of those, but then how can we know which one is the correct one? In the case of Kepler, of course, we know what's the ground truth, but in the case of new discovery, then we don't know that, right? So we actually, fun thing is that we also tried with Gemini. So Gemini was more clever, so it didn't try to generate a formula, it just to try to find the source of the data. So it found a website that contains this data and said, this is Kepler data, so the formula is Kepler. So at the beginning I just saw the result, I said, I'm impressed. But then if you look at the reasoning step, it was a little bit... Okay, so then our research question became, okay, how can we automate this connection between the canonical knowledge and AI-driven discoveries? And this brought us to another question that said, can we evolve over the classic scientific method? So our idea is to move towards a derivable scientific discovery. That is also the title of the talk, right? Because when we do scientific discovery, we don't want just to produce formulas that approximate the data. We want meaningful ones. And with meaningful, what I mean is that they are interpretable, we can verify them, they are grounded in theory, and how to do that, we need to combine somehow what we extract from the data, so the symbolic model extraction with formal reasoning. And so we want to be able to prove that a formula is correct. And if it's not provable, we at least want to find a distance to the theory that we already know, that is true about the phenomenon we are studying. So our solution was to create new ways of interpreting the scientific method. And of course, we started by looking at what's the classic scientific method. And here you can see is mostly based on manual hypothesis generation, either from data and verified manually on theory or vice versa, and the more data-driven machine learning regression way of doing things that is just extracting hypotheses from data, and then here we could have this agentic loop maybe. But what I will be talking today is the three methods that we're proposing, and I will talk a little bit in details of each of them. So the first one is AI-Descartes, and this one is basically we try to extract the formulas from the data similarly to the machine learning regression pipeline, but then we're testing on theory. So these two things are separate. AI-Hilbert is the second one. We said, okay, can we integrate these two things in one unique mechanism? And AI-Noether is the last one. So this one, we say, okay, what happens if the theory we know is true is not complete? So how can we recover the missing part of the theory itself? So in the first two, we generate a hypothesis, while in the last one, we given an hypothesis that can be generated with any of these methods, we try to fill up the gaps in the theory itself. Okay, so let's start with the first one. So this one, as I mentioned, we do first extraction from data, and then we test the formula that we extracted on the theory that we know is true about the phenomenon we are observing. So for give you this quick schematic of overview of how this works. So we start from data and from a theory. So from the data, we use a symbolic discovery to extract a listed order of hypotheses, and this one will have different error on the data. And this is how they're ranked. Then we take this ranking, and then we feed into a theorem prover, a reasoner, together with the background theory, and we obtain a re-ranked list of hypotheses. And this is based on the error, so how close these hypotheses are to the background theory. And then we take the top one, and then we can use this one for the predictions. Okay, so how we do the symbolic regression part? So we transform this problem into an optimization problem, which then we solve with the MI and NLP. And this one will try to minimize the fidelity on the data, given some constraints on the complexity. We impose a grammar, and then we set basically the primitive that we want to use. For example, if we want to use only a certain subset of operators, so we will find the formula that best approximates the phenomenon given this set of operators. And we can also impose some invariance and nonlinear numerical expression. So once we obtain formulas in this way, we want to test for derivability. So as I mentioned, we have the background theory. So the big assumption for AI-Descartes, which is the first method I'm talking about today, is that the background theory is complete and consistent. So there are no contradictions, and we know everything that we are supposed to know about the phenomenon, except the phenomenon itself. And then we'll see later how we relax this assumption with the other two methods. So, but then we extracted now a formula from the data, and we want to check if it's derivable with a theorem prover from the background theory. So, and we have two types of derivability. So the first one is just standard derivability. So we want to see if the formula is implied from the set of axioms. But the problem is that when you extract formulas from data, often they have numerical values, and these numerical values are not exact. For example, pi. We will not have all the digits of pi when we try to approximate it from the data, right? So, but for a theorem prover, this is difficult because this is treated as a numerical symbol, and if it's just different from like a decimal point, then it will not prove it, right? So this is why we can substitute these numerical values with existential variables. So in this way, we can check if the functional form is correct. And then we can still tune the numerical values with another round of optimization. So, and this would be the ideal world. We can prove it, but the ideal world never happened, right? So then what do we do if we cannot prove it? from the background theory. Then we want to have estimate of how this formula is close to the theory that we know. So then we think about two different functions. So one is the hypothesis, that is this green one. So the hypothesis is what we extracted from the data. And then the other one, I don't know if it's too small, if you can see, the blue one, this is the hypothesis that is implied from the background theory. So we don't know this explicitly because if we do materialization of the background theory, we can extract all the possible formulas that are derivable from the background theory, and the right formula should be there, right? But we cannot practically do that because as soon as we add arithmetic operators, we cannot ground everything because it's not even finite, right? So then we have these two concepts of functions. One is extracted from the data, one is induced by the theory, but we don't know it explicitly. But we can use a theorem prover to compute the distance between these two functions. And we computed three types of distance. The first one is looking at the points. So we look at the points of the data, and we compute with the theorem prover, or we approximate with the theorem prover the distance of these two functions on the point that we saw in the data. So if you think about Kepler, so the Kepler's law of planetary motion, so you have, suppose, a star, and you have planets orbiting the star. So the points will be the measurement of where the planet, how far the planet is from the star, for example, the speed of the planet, and so on. And we want to discover the equation for the period of the planet around the star. So these are the points that they were looking at. So but then we said, okay, maybe on the single points, the approximation is very good, but what happened in between? So with the theorem prover, we can also look something that is, let's say, between the mass of Jupiter and the mass of Saturn. So there are no planets on a mass that is in between these two, but suppose there is one, then we can compute the error. So here we take the maximum error in between the points. And the last one, we say, okay, what happened if in the solar system we had a planet that is much bigger than Jupiter, right? So what happens if we increase from some order of magnitude the size of the planets in the solar system? So we can check also there how the reasoning error increase or decrease. And this will tell us if a variable in the formula we discover is in the right place. For example, is a numerator instead of the denominator, and so on. So just to give you a concrete example on Kepler's law, here in this experiment, we considered three data sets. So one is for the solar system. So we have the sun, which is the star of our system, and you have the planet. Then we can have we have an exoplanet data set. So the exoplanet, you have different star systems. So each of them with different stars and different planets. The last one is binary star. So you have two stars in the same system. So as you can see, with the symbolic regression, we obtain a set of formulas that approximate the data in different ways. So we have different numerical errors on the data. And we can order them based on the error on the data, right? But then if we look at the reasoning error, we can see that for the solar system, the first one is the best one. So we have the one that minimizes both numerical and reasoning error. For the second data set, it's the same, so the ranking was still good. But for the last one, if you can see, the first one is very long formulas, right? Or even the second one is more compact, but as human, we can look at it and we say, okay, this probably is overfitting, so it's modeling also some noise, while the last one looks more reasonable. But how can we do this automatically? So if we look at the reasoning error, we can see that if you look at here, this one is the one that minimizes the reasoning error. So then, and in the case of the last one, we can even prove it in this case. So then we can see that if we have this assumption of AI-Descartes of complete and consistent background theory, then we can look at this trade-off between errors on the data and error from the theory. So, but what happens if we don't have one of these two assumptions? So this is why we start to look at how to integrate these two parts more, how to integrate these two components. Because in AI-Descartes, we do, first we extract the formula from the data, and then we check the theory. So in AI-Hilbert, we do these two things at the same time. But this also comes as a cost, because we need to restrict to polynomial equations. So in AI-Descartes, as long as you have a theorem prover that supports the operators you're considering, you can consider any operator. While for AI-Hilbert, we use a theory that restricts only to polynomials. Okay, so let's see, what time is it? Okay, still have 20 minutes. Yes, 15? Okay. Okay, so then AI-Hilbert is this unified framework where we try to extract formulas of this type. So it's a polynomial equation where we have a set of dependent variables and independent variable that is our target. And we want to do these two things: fit numerical data and be compatible with the background theory. So, but more in practice, what we're doing, we have still an optimization problem on three objectives. So the first one, we want to minimize the distance to the background theory. The second one, we want to be close to the data. And the third one, we want to find the equation that is the most compact possible. So for data fidelity, we all know what it is. So you have a set of numerical points, and we want to minimize some type of loss. And depending on the different norms and so on, we can have different choices here. For model complexity, also here, we don't want long formulas that overfit our data set. So what we do, we can take, for example, because we are considering polynomials, right? So we can take a look at the degree of the polynomial, or like the norm of the coefficients, or how many coefficients are non-zero, and so on. But the interesting part is how we compute the distance to the background theory. So to compute this, we use this nice theorem. So just in, how to say, more non-mathematical explanation of the theorem is that if you have two sets, one for equalities and one for disequalities, then we have that this theorem says that a polynomial is non-negative on this constraint set, exactly when it can be written as basically the multiplication of the axiom in the background theory with some polynomial multipliers. And these are called the certificates, right? So, and this is a nice way, because then we know how to build this formula as multiplications of polynomial multipliers with the axiom in the background theory. And in the case that this is complete and consistent, like the background theory, then we will have an equality, so this will be equal to 0, right? And this is the same case of AI-Descartes, but what happens if it's not completely consistent? So in the case of incompleteness, we just want to minimize this difference between our target variable and the set of multipliers, right? And for the case of inconsistency, that means inconsistency, you have some axiom that is inconsistent, right, within your background theory. So you want to exclude some of the axioms. So then we introduce some variables that can make one of these axioms equal to 0, because it will be the multipliers equal to 0. So then we can consider a subset of these axioms. And then it will apply the same principle as before. So, but in general, what is nice of AI-Hilbert? So here I want to show you an example for Kepler's law again. This is our toy example in the whole presentation, is that if we remove one of the axiom, in the case of incompleteness, suppose we have a complete theory, if we remove one. So we know exactly that we remove one single axiom. Then we can see that augmenting the number of points in the data, we can compensate for the missing axiom. So this is the beauty of AI-Hilbert, is that it really shows this trade-off between how much data you need and how much theory you need. So if you have a complete theory, probably you don't even need data, while if you don't have the theory, you need a lot of data, like in machine learning models. So, and this, it shows that exactly how many data points do you need to compensate for each axiom, right? So this is the nice thing of AI-Hilbert, because these two things are done at the same time. Okay, but the next question is what happens when we don't have an axiom, but we can still, using data, more data, we can generate the right hypothesis. Okay, so if we have the right hypothesis, then we might want to reconstruct the missing part of the background theory. So this is exactly what we did in AI-Noether. So for this one, so it's basically how to perform abduction in the field of scientific discovery. So if you look at this example, suppose we have a set of axioms, and then we have a conjecture. So now we can prove this hypothesis from the set of axioms. But then, suppose we remove one of them. Okay, now we cannot prove the hypothesis, even if we discover the hypothesis anyway, but we lose this automatic way to prove of that the hypothesis is correct. So then, in AI-Hilbert, we saw that, okay, we can still recover this hypothesis if we add more data, right? But now, we still don't have, we cannot prove that the hypothesis is correct. So then we want to rediscover the original axiom that we, at the beginning, removed. And this can be done with AI-Noether, basically. So if we have some very small assumption, which the first one is that, again, we restrict ourselves to polynomials. The second one is that we assume not have direct data for the missing axiom, because the missing axiom has also some variables that are not observed in the data, in the phenomenon itself. Because if we had the data also for the axiom variables, then it would be the same as just applying AI-Hilbert, and we'll have, we can generate it as a hypothesis. And then we also assume that the axiom that is we want to regenerate is simpler than the hypothesis, because if it was more complex, we could just directly derive the hypothesis from it. So given these single assumptions, then we can use primary decomposition to recover the original axiom. So more formally, if we have a set of axiom system which does not derive our hypothesis, that means some of them are missing, we want to study the reducible components of the variety that is defined by the background theory, so the partial background theory, and our hypothesis. But how we do this is we use the primary decomposition theorem, hence the name of the system, which states that that every variety can be written as a union of irreducible, irreducible varieties. So what does it mean is that if we have a set of axioms that define this variety here that you can see, we want to take out all the single irreducible components, and these are basically our axiom. So we can recover the missing axiom from the hypothesis. So just a quick example of our experiments is that we are considering here Einstein relativistic time dilation law. So I don't know how many of you is familiar with this experiment, but basically you have a light clock which is moving or is stationary, and you want to compute basically the distance and of the projection of the light once it comes back. So, and as you can see, in the relativistic scenario, we will have a time dilation law, time dilation, because the speed of light is constant. So if the clock is moving, we cannot add the movement of the clock plus the speed of light. And so suppose we remove one axiom, then we can see that both with AI-Descartes and AI-Hilbert, we can induce the correct hypothesis using some data, right? But we cannot prove it. So then, with the AI-Noether, we recover these two axioms. So basically, without having any information that the speed of light is constant, we can recover the fact that the speed of light is constant. So this is quite nice, I think. And here is another example when we remove multiple axioms. And here is the same. We remove some of the axiom. We can still derive the hypothesis function with the help of some data, and we can recover like a combination of the missing axiom. So we cannot recover often the single axiom separate, but we can recover a combination of them. And even in this case, this is Kepler law again. Even without knowing about the centrifugal force, we can basically abduce the formula for the centrifugal force with the condition that we applied the other two axiom on it. So it's basically a combination, but it still describes the centrifugal force. Okay, so now we saw this tree system. So AI-Descartes, which assume the background theory is complete and consistent, but is not restricted to polynomials. Then we saw AI-Hilbert that does the discovery from data and theory at the same time, but is restricted to polynomials, and AI-Noether, which recover the part that are missing from the background theory with abduction. So, as you can imagine, there are still many open questions, and because we have some limitation for this system, like the older system that I mentioned at the beginning for AI for scientific discovery, and I have many questions about this, more questions than answers. So, and now I'm open to your question if you have any.
A couple of different points. You mentioned an underlying theorem prover. Mm-hmm. Is there a specific system, or are you building theorem provers at the same time?
No, we are using like off-the-shelf theorem provers. So the first, for AI-Descartes, we use a theorem prover called Chimera, because it also handles some simple dynamic system. But depends on like the fragment of logic you're considering. Yeah. So, and depending on that, you can use any available one. So for example, if you just restrict, I just want the plus sign, then you might choose one theorem prover. If you want also some dynamic system, then Chimera could be a better option. Yeah.
Thanks for the very nice talk. I was curious about the distinction between the data coming from the differential equations and some underlying function. Now, is there in principle, multiple functionals might give you the same differential equations from which you do the remaining downstream tasks. But how do you uniquely specify the theory?
Yeah, so in AI-Descartes, we consider only when, because of this complete and consistent assumption, then we assume there is only one unique correct function. This is why for the other system, the polynomial equation, we don't do that assumption, right? So in that case, there could be multiple ones. But then we don't use this theory that we use for AI-Descartes.
And just a follow-up point, not all functionals, not all the symmetries present in the classical functionals might translate into the equations of motion.
Sorry? I could not hear you.
So not all classical symmetries appear in the full theory often, especially if it's a quantum theory. But there are ways to tackle those symmetries as well.
I'm not expert in quantum theory, but so I'm not sure I can really answer this question. But I mean, if you can express it as a constraint in the same, the same formalism of your theorem prover, for example, then you can use it. If, from what I understood, it's not possible to express it as in a closed form, then.
So usually the classical symmetries are they have the same kind of an approach, and they appear in the classical Lagrangian or action. But in a quantum action, often there are some symmetries which are symmetries of your classical theory, but not of the full quantum action. And usually we don't want those symmetries, but they lead to some conditions called anomaly cancellation. But they are also algebraic, and in principle can be treated by quantum.
Okay, so I can look it up more, but I'm not sure I.
Thanks.
Yeah.
So maybe I can ask. In your AI-Hilbert, if you drop one axiom, then you need to increase some data.
Yeah.
If you drop different axioms, the increased data is any kind of difference of this data.
Yeah, you need to add more data, right? If you drop more than one axiom. Of course, if you drop all the axioms.
No, if you drop A, you have an increased data set. A. If you drop B, that increased data B.
Yeah.
A and B set. Is this different with this?
Yeah, there is a difference because some axioms, they are more important than others.
Yeah.
For example, I'm not sure I have an example here, but sometimes you have like the equilibrium condition. So this is very simple formula. So what we notice require less data, while if it's something like, I don't know, the gravitational force definition, this requires much more data. So depending on the axiom, so this is what is nice for AI-Hilbert, because if you try to remove each axiom, you can see the different amount of data that is required to compensate from it. But you can also drop more than one, but then you need much more data. Yeah, yeah, we didn't study like if you remove two, for example, how this how the number of data points required, how this increase, but definitely it's different from different axioms.
Still in the abduction scenario to another, when you remove axioms, you maybe have some variables that are never seen to prove the F right. But how do you, when you want to infer the axioms, how do you retrieve those new variables? I mean, how do they come into the form when you want to specify the axiom?
So yes, this is actually a very good question because we thought a lot about it. So if you want to recover the variable itself, that is very hard because if you don't know it exists, then we don't do any kind of variable invention, or because in logic there is this thing of predicate invention, variable invention. So we don't do that at the moment. My guess is that if you try to remove basically one variable from, like, let's say you remove two axioms, and only these two axioms contains a variable, then the result that you will abduce is the combination of these two axioms, which will kind of cancel out this variable. So it will be the combination, so the variable will not appear there, but you just retrieve the combination of the axioms, not the two singular axioms.
Okay, because the variable doesn't appear in the final F. Okay.
Yeah. So it's kind of like you combine the two axioms, and then this variable probably will kind of cancel out some way.
Well, what if okay, but if the variable is in the F to prove, you initialize that variable that then is supposed to exist.
Yeah, so that will
because when
appear.
you remove it from axioms, you never see it, but you know